I want to welcome everybody to this webinar from the American Nuclear Society's Risk-Informed, Performance-Based Principles and Policy Committee, RP3C. My name is Prasad Kadambi, and I'm chair of RP3C. The purpose of RP3C is to help modernize ANS standards. Modernization has come to mean that risk-informed and performance-based methods are employed to overcome the difficulties that we all know about with purely deterministic and prescriptive methods. We have been calling these methods RIPB approaches. RIPB has now become established through the Nuclear Energy Innovation and Modernization Act, which explicitly recognizes this approach. There's a lot of guidance available on RIPB approaches, but most people have not had reason to become familiar with the guidance because the conventional approaches still dominate most things that we do, including standards development. RP3C initiated these community of practice webinars on RIPB to enable practitioners of RIPB approaches to share their knowledge and experience. We had the first of these webinars in February on the subject of employing a systems engineering framework for enabling use of RIPB methods. Today we will be hearing about RIPB methods associated with the project that is being carried out by Oklo Incorporated. Caroline Cochran has graciously agreed to make this presentation, and I'm very grateful for her because I'm sure that at this time, everybody on the project is extremely busy, and for you to take the time to make this presentation is very helpful to us. So Caroline, I'd like to have you take the presentation from here on.
Thank you. Thank you, Prasad, for the introduction, and thank you, Pat, for helping organize. It is an honor for us to get to present here today. I am not an RIPB expert, I wouldn't say, but I'm here to present about Oklo's experience with these, in particular the guidance that Prasad mentioned, and implementing it. Oklo was actually the only company to pilot the guidance with the NRC in 2018, and of course has since then submitted our first license application to the NRC, which was accepted in June of this year. So without further ado, I'll just get started here. So yeah, a little bit about Oklo. You may or may not have heard of us. We're still a really small company. We're developing advanced fission plants, and we actually had the first ever modern venture-led Series A. So it's a type of private fundraising. We actually have not received any government funding to get to the place that we are at currently. We were granted a site use permit from the Department of Energy for the INL site late 2019. We were also selected to demonstrate reuse of fuel at INL. So with that, we had both a potential site for our first plant as well as fuel material for our first plant. And we became the first advanced fission company to submit a license application that was accepted by the NRC, and that occurred, we submitted in March of this year, and it was accepted in June. So we're currently in our, what's called phase 1 of our license application review. Here's just a slide talking about some different media that have covered us. It's been interesting to see not just technical publications be interested in the work that's being done in advanced fission, but also artistic or architectural ones, in addition to finance and technical. So a little bit about the Aurora, which is the plant that we submitted the combined license application for. The Aurora has 1 to 2 megawatts electric output depending on use case, and So obviously very, very small, much smaller than is typically being considered. Certainly much smaller than the AP 1000 or most commercial operating plants. It was a concern of ours how for many years, how the NRC staff would be able to digest this and treat it differently. It's almost like a research reactor size, although obviously a commercial plant, which falls under commercial regulatory scheme. 20 years between refueling, so our full license length that we've applied for is 20 years, and there's actually no refueling intervals in there. So that's yet another thing that's unusual for the NRC, but also presents benefits for uptime as well as potential security benefits if you don't have refueling occurring frequently. We call it an advanced fission battery with solar. Part of the reason why we sometimes use that term battery is because you can see to the right there on the screen, it's all, the whole core and what we call the primary portion of the plant is located inside this module that goes underground, and it basically stays there for 20 years. There is ability to switch fuel out if needed, but the idea and the way the license is put together is that refueling is not required during that interval. So it almost acts like a battery. You charge it with the fuel and it produces power for 20 years with a high uptime. We do have solar panels on that building. I'll show you there. You can't really see them very well, but the kind of stripy colors you see on the building. The idea is that solar can provide incidental power for the site, but also demonstrate that, nuclear can work together with renewables. We also can utilize used material or waste. I know the term waste is what's commonly used, but it's really not waste if it has so much energy left, of course. So typically in the nuclear community, you use the term used fuel or different terms like that. But in essence, not only can we use that, we're looking forward to demonstrating that more holistically in the supply chain, but also our very first of a kind core will actually be used material from a prior reactor operated at INL. So I mentioned that it's very small. There's a lot of other characteristics that are very different from current large light water reactors and require a very different perspective and just mindset, putting on a new hat when you look at the Aurora versus current plants. So you can see there the differences in power output on the order of 100 to more times the amount of power output, much longer refueling cycle. It says none because our current license is the full length of our refueling cycle. Radionuclide inventory and so on and so forth. We're not pressurized, don't produce hydrogen in the same way. There isn't really a cooling loop or flowing coolant. The heat pipes transport heat, so frequently we don't even call it coolant or cooling. It transports the heat from the core to the power conversion system. And then, we don't rely on electric power in order to achieve safety characteristics. And we have, of course, a negative reactivity coefficient. So many characteristics are very different. From top to bottom, we had to really look at things differently when we do safety analysis and how we kind of assess things. And I think that's what I'll be sharing with you is how that kind of intersects with the considerations of both being risk informed as well as performance based. So as Prasad mentioned, we did a pilot of what was then the draft guidance 1353 and has now been issued as regulatory guidance. And it was called the Licensing Modernization Project, so LMP for short. We turned that into the NRC in 2018 and had some follow-up meetings. So that's now called Reg Guide 1.233. And the idea of this guidance is to allow for companies to utilize a new process in order to do selection of their licensing basis events, classification of components, as well as a formalized way to assure defense in depth adequacy. Defense in depth has been a concept that the NRC has implemented, for some time. It's a kind of a policy of theirs, but there isn't a clear regulatory requirement, and it could be used historically as almost like a gotcha. Well, do I really need this? Well, for defense in depth, you need this. So the idea this draft guidance was to allow for a definitive process that can say, look, here's my assurance that I did consider defense in depth, and basically have an agreement between both the NRC and the applicant that if you meet this process, you will have assured defense in depth, and there's kind of no more gotchas or kind of confusion between the two parties. So that's the idea of the guidance, and I'll talk a little bit about how it is unique in ways that may not be obvious, and in particular how those maybe almost uniquely came to light because of the Aurora pilot of it. Now, when I say pilot, there's a process with the NRC where if you try out a new type of guidance and you're the first of a kind, they do what's called a pilot program where the fees aren't assessed in the same way, and they invited the industry to pilot it with them. We were the only ones to pilot it directly with the NRC. However, there were a number of companies or designs that did versions of what they called tabletop exercises, exercises of the methodology and the guidance with basically an industry-led and DOE-funded team that kind of conducted these tabletops. So that's what I mean when I say piloted. Our engagement was directly with the NRC and intended to actually flesh out what this process would look like in basically a draft form of our application. So it was a very interesting exercise that not only implemented LMP, but also a wholly new application format. That won't be the subject of my talk here, but that was, if you take a look at it, you'll see kind of the format in which that was submitted to the NRC, and you can see some of that online. So to get back to it, some of the unique characteristics that we found with this process, the process is risk-informed, not risk-based. I think that may be evident from the title, but one aspect of that is that deterministic analysis is a major portion of this, and that deterministic analysis is then suggested to be plotted on a frequency consequence curve. Of course, deterministically failing certain components shouldn't have a frequency component to it, so it's a bit of a challenge. Just in the beginning, the goal is to stay within certain the good side of the frequency consequence curve. But when you're deterministically and arbitrarily failing certain portions, and this is in the defense in depth portion of the guidance, it's been plotted on this curve, but that's something that we've essentially taken issue with somewhat. Just take a drink of water here. The process is, yeah, go ahead.
No, I apologize. I thought if you were taking a break, you might want to answer a question.
Sure.
But we can, why don't we wait until after this? Mm-hmm.
Yeah, okay. Yeah, I'll just do this slide and then take a question. The second thing we found that was unique or interesting is that the process is not intended to handle passive or inherent features of plants. Really was developed around the idea of active systems. Even passive systems was kind of ruled out of this process, at least in the early times when we were doing the piloting of it, which is obviously a major feature of advanced fission or non-light water reactors that are looking to come, and to work with the NRC on licensing or certifying or something their designs. And in particular, the Aurora has what we call inherent features that kind of keep it from even getting to events with consequences. And I'll mention more about that in a second. Arbitrary failing of what we call inherent or physical aspects of the system can produce unrealistic results. So that can be like, arbitrarily failing the thermal conductivity of the fuel, which allows it to stay cool. So that's a challenge. It might degrade, but just suddenly assuming that conductivity doesn't exist is a challenge. And some of that comes down to how you interpret the guidance, but because it is really set up for active systems, failing of inherent or passive systems can be difficult to determine the correct way to do that. Lastly, the defense in depth portion, I mentioned earlier how it kind of ends up deterministically failing certain things, but it also, there's tables that essentially create ways of categorizing components based only on whether their failure increases the frequency of an event, not necessarily the consequence or the combined risk. Of course, everyone on this call probably knows that risk is frequency times consequence. And so to isolate out only the frequency portion, we believe is a challenge, and it comes from a history of large light water reactor as well as potentially large non-LWR space where a consequence is assumed to be the case. And so really all you have to consider at that point is a frequency. But we actually, with this plant and its inherent features, had a number of events that don't result in consequences. And so we found challenges with the just considering only changes in orders of magnitude of frequency in that table versus kind of the combined risk aspect of the holistic risk aspect. Sorry, so Pat, did you have a question?
Yes, there is one question, and it is actually from an anonymous attendee. I will go ahead and just summarize the question, and I assume that attendee will be able to further explain it. And it's just a question, I believe, about something you had in your presentation: can utilize used material being waste? And it says, does that mean SNF intended for Yucca Mountain, or depleted uranium, or down blended HEU, or surplus weapons grade plutonium?
Yeah, kind of all the above. The first utilization, as I mentioned, is basically processed fuel that came from the EBR2 reactor. So obviously already high enriched uranium. So that's uranium-10 zirconium fuel, and so that's currently undergoing processing at INL and will be available to us, hopefully, hopefully lines up perfectly that we have that material in time as we complete our licensing progress. But what we're looking for in the future is being part of a recycling that actually allows for utilization of SNF, like from commercial reactors. We're also looking at how to utilize other types of used materials. So the fast spectrum allows us to have a lot of resilience against impurities, and honestly, plutonium is also a great fuel. We can utilize, weapons materials and turn it into clean energy. Of course, though, plutonium carries other burdens as far as security and other aspects. So I'd say that's definitely something we're looking at, but not expecting to implement in the near term. But really being a part of hopefully what we see as a complete supply chain that involves recycling nuclear fuel is something that's really exciting to us and something we're actively working towards.
There is also a question from Robert Hayes, and I can let Robert Hayes go ahead and ask that. Robert, are you able to unmute?
Sure. Yeah, it sounded like you were saying that you did a perturbation on the frequency to compensate for not doing a consequence approach for the outcomes. And that didn't make sense to me, so I'm assuming I understood it wrong. Could you please clarify?
Yeah, I'm not certain if I got the question right, but I'm going to start answering and then maybe you can interrupt me. So what we did was try our best to implement the process as it was laid out by the licensing modernization plan and the draft guidance as best as we knew how. So while there might be things that seem like they didn't make sense to you, it might be similar for us, and some of which have potentially been addressed, but most of which I don't think have come to full resolution. What I would say is the LMP guidance is now kind of in what they've called LMP phase 2, which is considering how that might inform portions of an application, level of detail and portions of a license application to the NRC. So I think it's more or less, process is more or less set in stone. But actually, do you mind repeating the question?
So it sounded like what you said was that in not evaluating the consequences of an outcome, you compensated for that in your defense in depth approach by doing perturbations in the frequency, looking at different frequencies for that particular event. And the logic of that, I wasn't able to see through how that argument would be made.
Yeah, that's kind of, I think that's maybe a misunderstanding of what I was trying to get across. I think what would be important to note is that the process prescribes different there's a whole flow chart, and I didn't copy it here, but of different steps, and some portions are supposed to be deterministic and some are supposed to be more risk informed, and you kind of perform the PRA and so forth. But we did, in the end, we didn't do what I think you're describing there. But what I think you're saying is like we perturbed that in that way, but it was really just considering only the frequency, not the consequence, was only part of the basically filtering mechanism for how you categorize components. So you do all of the above when it comes to doing risk-informed, analysis of the system. You also do deterministic failures of the system, and then the process part of it is where you take those results and utilize tables and so forth to determine how you use those results and actually categorize your components. That was the part we took issue with, was considering categorizing components by considering how their failure affects frequency alone, without considering the holistic consequence, the actual risk, which is the frequency times the consequence. And I think part of the reason why the methodology came around to be like that is because many of the developers had a background in light water reactors, and so consequence was kind of assumed. And so that's basically how they kind of developed this one table that I don't obviously have on this slide, but it's part of establishing SSCs that are considered non-safety related but special treatment. And yeah, so hopefully that helps.
If I may, Caroline, I don't want to interrupt you, but this whole issue of how the LMP guidance in NEI 1804 can be applied in specific cases is really a topic all by itself. And as I mentioned to you, we have coming up some community of practice sessions, at least one of which will address that. So why don't we hold that as a thought for future sessions? So you can go ahead. Otherwise, this thing can just go on forever.
Yeah.
So.
Okay. All right. So analyzing deterministic. So basically, I'm going to go through each of these bullet points in separate slides. One of which being analyzing deterministic failures. The process of categorically failing SSCs is deterministic. There's really no associated failure probability, and so that should no longer be considered in risk space. We believe it's inappropriate to evaluate deterministic sensitivity analysis against risk measures, and you really need to evaluate that against deterministic criteria. Failure barriers, or kind of the failure of inherent characteristics, is one thing I mentioned before, but passive or inherent characteristics don't necessarily disappear. They may be degraded. It's certainly aphysical. So for instance, if we were to suddenly assume that the module shell was just gone, without considering a mechanism by which it'd be degraded, that's just really not a realistic thing. And the kinds of consequences you come up with because of that are similarly aphysical. So a challenge in modeling that, it's also a challenge as far as really not having any analog to physical reality. So again, appropriate to analyze barriers as well as degradation of inherent characteristics and levels of degradation, more than just assuming they kind of disappear or 100% fail, I guess. And then lastly, the idea of zero consequence events is more or less left out of the methodology. And I think now I've said this a couple of times, but the defense in depth portion is really based on frequency changes regardless of consequence. And risk is really composed of frequency and consequence together. Low and zero consequence events either nullify or substantially reduce total risk, and categorical classification of components based on frequency alone is illogical. So I'd say the pilot results from piloting DG 1353 was that, even based on kind of what we considered on our part to be conservative interpretation of the requirements. And again, this was for internal events. We scoped out external events, but for this pilot, but no safety functions or safety-related SSCs were found, which was certainly a topic of major conversation with the NRC and very interesting result. But we did result in many NSRST. So I mentioned that non-safety related with special treatment SSCs. So this is due to the kind of the scheme that said that if it increases frequency by X orders of magnitude, and there's kind of a table that says, okay, if it crosses this threshold, it would be considered an NSRST. However, some of those results could still have zero consequence and yet end up being in these NSRST SSC bucket. And the other challenge with this is it's unclear the kind of regulatory burden that should or would be applied to NSRST. Certainly with safety related, it's clear you have to implement, Appendix B quality assurance throughout the process and a lot of people don't remember this, but from design onward. So how you do your design, how you do approvals to changes to design, how you document that, and onward for something that's considered safety related has to be followed all the way through. It's unclear if NSRST has to have a similar burden for how everything's documented and controlled and assessed, and all the way through, of course, to the supply chain and so on. Of course, applying Appendix B is kind of a big go no go as far as significant burden on the whole supply chain for that SSC. But also there's other potential requirements, and I'll talk a little bit later about how we apply programmatic controls. Of course, QA is one of them, but it could also have to do with how you do pre-operational testing, startup testing, tech specs related to that SSC, and so forth. So I think we found that as a challenge that we would end up with nothing that's safety related, but many NSRST of unclear, how that should be handled. So in the short of it is that we would anticipate similar challenges for all non-light water reactors to implement the process. Of course, Aurora is unusually small and simple and has many events that are no or low consequence, but actually many advanced reactor designs of various sizes have a similar situation. And I think some of that was illuminated through different tabletops, but done by different companies. And I'm sure that more of that will kind of come to light, and how to treat that will be further evaluated. As it stood until a small revision was made, the role of the, sorry, I'm blanking on the word, but the panel of experts, the IDP, could add classification to an SSC, but not remove it if it came out to be kind of, the panel of experts decided it was basically overclassified. So there is no pathway after you've basically gone through this process and ended up with a probably disproportionate amount of NSRST SSCs to actually reverse that, even if a panel of experts kind of determined that that is unrealistic. I think there's a lot of faith in the process on the part of the guidance, and so the IDP has the opportunity to add classification or additional burden, I guess, to an SSC, but not to remove it. But I think that's something that is or is being looked at being changed. But it was something that we saw as a challenge. But it's not just these are the focus of what I wanted to bring up here, and kind of our key challenges we thought a range of non-LWRs may have with this process. But beyond that, there's actually several other issues. For instance, the way that the guidance is written essentially brings beyond design basis space into consideration of design basis space. And of course, we are concerned about that because of how you would kind of basically have additional QA burden, Appendix B burden on even just starting with design and analysis early stages of doing that work. If it's even what is traditionally been kind of ruled out as beyond design basis space is now kind of considered in that way. The interest in that was to avoid cliff edge effects and to be holistic in the guidance, but we worry that that is essentially amounts to an increase in burden over already safe kind of practices for existing plants. So that's what I want to highlight with that. Last for this kind of section, and then maybe I'll see if there's another question or two, is a new way. We really felt like there needed to be a consideration of a new order in which to consider the risk triplet. Instead of what can go wrong, then how likely is it, then what are the consequences, talking about what can go wrong and then what are the consequences first before trying to establish frequency, which can be a challenge when you have first of a kind reactors. You don't have a broad database of data in a wide range of ways. If you first kind of assess what the consequences could be before the frequency, it can actually rule out a number of events that essentially have no or extremely low consequences. And we believe that that order change really increases efficiency for how you would evaluate advanced fission with inherent safety, and may have many events that don't result in consequence. In other words, instead of the risk triplet kind of as it is, but almost asking first, are there any consequences, may be a key question for advanced designs. This enables evaluating credible events with possible consequences found deterministically against performance-based metrics of dose in the regulation. Risk can be assessed for credible events with consequences, as shown, as we did in the Aurora PRA. So we'll be talking a little bit more about how we ended up using kind of more of a deterministic approach with some risk insight as almost as a measure of defense in depth, but really focused on more of the PB part of the RIPB when we got to our final application. So now might be a good time to pause for questions.
Thank you, Caroline. I do have two questions. One was actually submitted just as you had started back up, so it might be a little delayed. That is from Don Spellman, and he is questioning the potential maximum thermal output of the design. And Don can clarify if there's any clarification needed.
Okay, so I'm guessing there's not further clarification. So you said asking what the maximum thermal output might be?
Correct.
So I'll just go back to that slide really fast. So this is the thermal output of the Aurora, about 5 megawatts thermal or less compared to thousands for current large light water reactors. This is kind of the difference. One way to put it a little more concretely might be to illustrate that this is actually lower in thermal output than the MIT research reactor. I went to MIT for grad school, so my office was, I wouldn't say on top of, but beside and above where the reactor was. Another way that you can kind of think about the thermal output is how much decay heat does it produce. And one thing we put out that's maybe seems a little cheesy, but it puts in concrete terms for people. After a day, the decay heat output is about like a large riding lawnmower. So definitely, some heat, but not like has been considered, really had to be accounted for in many other plants to this point. So it's much more feasible. And when you can start talking about your heat output for decay heat and numbers of hair dryers, it just it helps put in perspective the smaller challenges related to keeping it safe and low or zero consequence.
Thank you. So we do have another question from an anonymous attendee. The question is, it's interesting that the LMP process yielded no safety-related SSCs. What did your DBAs look like? And I guess this anonymous attendee may clarify if they so wish.
Yeah, so I'll start with a basic look at that. So, you know, the DBAs were really assessed deterministically, and the way that the process led to, there's not really an event that comes out that results in a dose to the public, and so that's you know, it actually didn't result in any dose, and the reason for that is because you have to have fuel melt in order to have release, and because of the inherent characteristics of the system, that isn't really reached. And so I'll give an example. Granted, a different type of reactor, much larger and some different characteristics to it, but the EBR-2 reactor, if anyone's familiar, the sodium fast reactor operated in Idaho, and again, the same one that we'd be getting their used fuel for our reactor. They did experiments where they did they completely shut down rods out of the reactor and shut off the coolant supply at full power, and it didn't have any fuel failure at all. It continued to operate that same day. They also similarly, they did other really major tests that same day. There's no fuel failure, and actually that year, the EBR-2, which did sell some amount of power, of course it was still a research reactor, but actually it had a higher uptime that year than the fleet did at the time. There's incredible resiliency to this type of metal fuel, as well as when you have a small, fast system that's tightly coupled with abilities to, you know, conduct in the way it does, reduces abilities for hotspots. And so the range of accidents analyzed can't come to a point where there's fuel damage. And that's really backed up by that experience, I think, with similar fuel type, similar fast reactor design, actually much, much larger. So you can kind of see how those fundamental feedbacks lead to a place where fuel doesn't end up melting, and so there's no essential consequence, and that's where that is. But what I will be doing in this next section is talking about how we do assure certain characteristics that have to hold for that to be the case. If that's a good time for me to continue on, maybe we can continue
yes,
on.
in fact, Caroline, I would say we'll hold off on the questions
Okay.
Until you finish at this point.
Okay, very good, thank you.
Yeah.
Okay, that works out well. This next portion goes well altogether. So what did we do as a result of that for the COLA? And I'll be walking through that. So we went directly to a combined license application. So we didn't do a design certification first, or a construction permit first, or some of these other processes. Because Oklo is anticipated to be the owner and operator, we could be the licensee and go straight to the combined license. There have been a number of things we've done differently with the NRC, just to give a picture for how the interaction's gone over the years. For one, we had a novel QAPD approved by the NRC. Actually, we received the final SER this year, but have been working on various quality assurance plans with the NRC for the last several years. That actually covers both the design and the construction scope, and utilizes NQA1 in kind of a different way, but largely looks very similar to what's been done before, but the way it's implemented is a little different, as I'll illustrate here in the following slides. We were able to work with, the NRC actually assigned a core team to the project, so that enabled us to have some continuity of staff involved in our pre-application and even into our actual application review phase, which I think really enabled us to not have to keep recapping things instead of just really moving forward, because we had that continuity of staff. We didn't have to keep going back to ground zero to build up on knowledge and information of the design and the project as a whole. We're able to manage the project dynamically with the NRC staff using a licensing project plan, which enabled us and them, I think, to do budgeting and planning in a better and more efficient way. So we were able to get through pre-licensing, I think, more effectively than past companies. And even so, it took us a little over 3 years of pre-application before we felt we were ready to move forward with the actual application. Simple safe design means few, if any, safety-related parts or issues, which I'll talk about more. So one way to look at it was how we implemented the LMP process, which actually, to my knowledge, is the only public version, publicly available version of doing the defense in depth portion of that guidance. I think they are working on implementing that in a future tabletop, or they may have done it in tabletops that were not released. So for now, we've done kind of the most holistic implementation of that guidance. Through that, we came out with no safe related parts. And we also kind of came at it from a couple different ways, which I'm about to talk about, and still came to the same conclusion. So I'll talk a little bit more about that. So the challenge here for our first application and for non-light water reactors broadly was meeting the currently applicable regulations while the design actually meets the regulations inherently. So because of those things I just was mentioning about really not having releases and therefore not having doses through even really major events, events that are much more significant than the current fleet is licensed to, how do we kind of set out what is important in the license application, what isn't, how do we ensure that it's tracked and the as-built and as meets the as-designed performance. And instead of essentially giving what I'd call binary dumb tags of SSCs as either safe related or not, really assessing what key assumptions or parameters around those SSCs must hold and how those parameters are tracked and assured. So we feel like this is actually a more holistic process to really ensuring that the safety that we're talking about in these systems is actually ensured all the way through the process and even in operation. So here's a little flowchart of our design and analysis methodology. Of course, it's iterative. You do design, you do analysis, you find the risk insights and hone the design and so on. Systems were initially designed to safety goals and keep iterating on those safety goals as well as performance goals and etc. The performance is analyzed under many different event types to find the maximum credible accident, and we did analysis for kind of event categories as New Reg 0800 lays it out for existing light water reactors, historical event types for non-light water reactors, so looking at the history for EBR2 or PRISM and different types of non-LWRs and seeing if there's any insight or types of events there that applied to the Aurora design, as well as extensive analysis of different external hazards. Of course, there's about 40 different event types that fall under external hazards. We utilize PRA throughout the process, we actually utilize dynamic PRA throughout our design process, but our ultimate PRA was a static one that was the insights of which were described to the NRC as required in the regulations. And it was essentially used for an added layer of defense in depth to the determination of the MCA. So essentially we found the worst or most bounding maximum credible accident through that deterministic analysis of those different event types, but then added on to it anything that was determined in the PRA as being essentially within the realm of credibility, which we essentially cut off at 10 to the negative 8 or so. Key parameters that are essential to assuring safety is the design base, we call design bases, and we'll describe how we use design commitments to assure these design bases and how programmatic controls ensure that is assured. So here's kind of a similar description, but a different flow chart. So the design bases are the characteristics of the system that ensure the safe operation of the reactor. The design commitments are the specific commitments made to ensure the design basis is met. So I'll give an example. Maybe a shutdown rod has to fall within a certain length of time. And we know that that's a key characteristic, so that becomes a design basis, but the commitment is that specific amount of time. So like, let's say a number of seconds or something like that. And the programmatic controls are how you ensure that those are met. So how do we know it's actually falling within that number of seconds? So here I'll kind of just flow through it. It's kind of a useful walkthrough. And to the programmatic controls. So programmatic controls include the quality assurance program. So applying quality assurance to a certain key parameter design basis that basically becomes your critical characteristic that you have to assure in the QA. Also, pre-operational tests can assure certain design bases and design commitments are met. So a pre-operational test to determine, okay, is this shutdown rod falling in this number of seconds? Similarly, startup tests can do that and confirm it upon startup. ITAC are another method of programmatic controls, as well as technical specifications, which are in place throughout the operation of the plant. So in summary, the FSAR describes that, as part of our combined license, it describes each system, provides the design bases and the design commitments. It also provides assumptions and key parameters in the analysis, confirming the sufficiency of those things and ensuring safety. The FSAR, the very end of it is the PRA that is required by regulation to be submitted as far as insights gained from the PRA, and that was used for defense in depth as far as our determination, as I was mentioning, of the MCA. The design process is iterative with insight from risk, but PDC actually, so principal design criteria, you'll notice that's on this slide but wasn't on the previous ones. It's actually another way to look at this and consider, okay, from the fundamental safety functions point of view, what systems are we using functionally to meet those? And of which of those, which are we relying upon or essentially crediting to function, and they all ended up being inherent systems. So even if you kind of look at it from the systematic perspective, you can kind of come at that as well as functional, so the fundamental safety functions. And so it's very interesting that both through the progress of the LMP pilot as well as through the functional derivation of design bases from principal design criteria, as well as the systematic approach of looking at the systems and determining which key parameters fall out of those, none of which ended up being active systems that we're relying upon to assure safety. I will say, we assume like large light water reactors that one shutdown rod doesn't fall in, and that was the insight from the PRA on probabilities that could be within the realm of credible, but multiple system shutdown was not determined to be credible. There's no common cause for that, and so that's kind of how that was shook out for determination of the maximum credible accident. Ultimately, the Aurora INL COLA is primarily performance-based to meet the regulations and utilizes a primarily deterministic event analysis method while incorporating risk insight. So that is the conclusion of my presentation. Thank you again so much for allowing us to present today, and it'd be interesting to hear further questions as we have time. I'll defer to you, Pat, as far as figuring that out.
Well, as long as you have time.
I guess we'll keep going, to the extent that people are willing to participate in the discussions. I guess I'm sort of, this is the first time that I've heard about how the Oklo approach matches up with what I think of as the performance-based approach, attributes. The only thing I would observe as, one of the people that developed the guidance on this is that you could have used the concept of margins, especially physical and temporal margins, I think, to better effect. But, that's just listening to you, Caroline. That's the observation I have. But we do have some questions, I think, that have come in through the Q&A. Pat, I'll let you just go through them one by one, and we'll see how long it can go. So.
Great, thank you. The first question is from Franklin Hope, and it said, why can't the research reactor licensing process be used for the very small reactors?
It's an interesting question. The main reason is it's not for commercial reactors, and we are intending to be a commercial plant. There are stipulations that say research reactors can't fundamentally make more income than they cost to operate by a margin of, so they can't make more than 50% of what they cost to operate. So we are a commercial reactor, so we fall under that. But even as this reactor is small, like a research reactor, we really wanted to work forward on a path to having all kinds of different applications for plants that even maybe don't look as similarly to research reactors. I would say too, there's maybe still a surprising number of requirements that would still need to be, I believe, changed substantively for research reactors to move forward in a productive way. So either way, we saw challenges to how that would be applied to a commercial, a micro reactor that is also commercial. So we certainly knew fundamentally that it was to be a commercial reactor regardless. So this was the path that we needed to take. There are some insights and some precedent, I guess I could say, that we point to occasionally with the research reactors, but unfortunately most of the existing regulations or guidance for research reactors are not directly applicable in the way you might hope.
Very good. I'll go on to the question by Ralph Hill. He may need to clarify this. The question is related to risk triplet. He said, if you consider early qualitative hazard evaluation, probability is usually H, M, or L, and the screens out events. Events not screened out would later be quantitatively evaluated, where determining frequency would be more detailed analysis.
I think what you're saying is, yes, the typical process that it follows, but it is not the most effective that we've found for analyzing plants that have a substantive number of events that result in no consequence. So that's why we really propose this kind of, I guess, somewhat inversion of how the risk triplet is considered and looked at. I hope that's answering the question.
Hi, Carolyn. This is Ralph. No, I understand what you're doing, and it caught my interest. But again, if early on you in the plant design, you're going to screen out a lot of things with just a risk matrix. So only those with significant consequences would fall through that screening process to have to then determine more detailed on what the frequency would be, et cetera. That's my point. So do you really need to invert the cycle?
Yeah. Yes, I think that you're correct that the process as it's laid out for the LMP guidance would be better served doing that kind of screening method first before the way it is kind of laid out as it is. So point well taken, that you could essentially do the inversion of the risk triplet by just doing a screening at the beginning of the analysis.
Thank you. I enjoyed your presentation, and you got some interesting concepts. So,
Thank you.
I don't know what standards you may be invoking in your design. I've been with ASME closest standards in the nuclear side for over 40 years, and we're wrestling right now with a couple things. One is I'm chairing a committee developing a plant systems design standard, which is very similar, has a lot of similarity with the process you were showing me. Be interesting discussing with that, or even getting participation by maybe someone from your company on our committee, because we're writing, it's a brand new standard. It's designed basically for high hazard facilities, but including nuclear, but also petrochem, chemical, et cetera, but looking at, and from a nuclear perspective for the new plant designs like yours. So that would be interesting to have. So I'll my email is hillr@asme.org if you would like to send me your contact info. The second area we're wrestling with, and it very much right now at the high levels within ASME, is a quality assurance program that's appropriate for the new reactors, and recognizing that we need to not take them from a light water approach, but look at their actual safety case. And that's we're just beginning on that road. So you mentioned a quality program that you developed with the NRC that was sort of unique. It might be interesting that we could get you to help offer that perspective to us as we go down this road.
Thank you. Thank you. Yeah. Really would appreciate the chance to give any, I don't know, feedback that we've seen from our progress. I think one thing I would say is we're broadly sometimes concerned about the progression of standards before there even is an industry. So we've submitted a license application, but certainly nothing's been built and operated from us. Other developers are further behind. And I think standardizing some things can be prematurely, can be almost more detrimental than helpful. But I can see where it can be helpful to the extent that, you know, those considerations are taking effect. So I really appreciate that you're reaching out and offering us to give feedback from a developer's perspective. Yeah, for quality assurance too, I think, you know, the Congress has really pressed on NRC to develop a Part 53, and I think it's yet to be seen how Appendix B could look in that part. Or in, you know, if Part 53 just refers to Appendix B as Part 52 essentially did, or could it be looked at entirely differently? And I'm hoping that a really fresh look will be taken at all of that, because it's essentially, I think, an outdated concept that was really put in place before broadly manufacturing started implementing, you know, the ISO's quality standards. And I think, you know, manufacturing has come a long way since the 1970s or 80s or so. You know, broadly, you look at other industries like automotive industry and things like that. It's just really changed in reliability and Six Sigma and all that kind of stuff. So hopefully, you know, this Part 53 really takes into account that in a smarter way of assuring quality than kind of the methods that were developed decades ago. So appreciate your comments.
Yeah, and that's where we're coming from. We know the NQN1 is developed for light water reactors, and the reactors like yours, definitely, it's just not applicable as it stands. And we recognize we need to do something with that. So.
Yeah, yeah.
So, Caroline, as an organizer of this, I'd like to just take the prerogative to address, I think, an issue you mentioned, which to me poses a real problem to our standards efforts. The idea that, you know, standardization is somehow has to happen only after you know, an industry has developed some kind of an operational record, as it were. In my view, that is not a correct view of the kind of contribution that ANS standards can make. Because what we would like to do is use standard methods that have been employed in other fields, perhaps, where it has been shown to be successful. And to some extent, you know, those methods can be brought into the nuclear, but given the constraints that many developers, you know, and investors face, it's unlikely that they will bring in some of those methods, you know, because it's going to take money and effort, and sometimes they can't afford to invest that. So, I mean, I feel that ANS, you know, can develop standards that are useful to industry, even though industry itself hasn't recognized the need for some of those things. So anyway, you know.
Yeah, I'd be happy to speak to that. So I think, you know, you're kind of bringing up two questions. One is, does there have to be operational or kind of experiential experience before something should be standardized? And I think that can be done prior to any experience taking place for certain reasons that are preemptive or so forth. I do think it presents a challenge to try to standardize something that hasn't yet been done. But to the second point, which is, you know, I think how do developers do the process they're doing? What are the insights they're seeing? What are the licensing challenges? You brought up investors. What are investors looking for? What are customers looking for? And I think all of those things are really essential. And for a company to be successful, they need to prioritize what's valuable to them. You know, believe it or not, I actually worked a little bit of research in standards 15 years ago in automotive standards. And you see automotive companies coming together, even though they have, you know, different interests and different customer sets, competitive interests, even different investors or parent companies. And they would come together for things that they found to be mutually beneficial and part of a needed infrastructure. I think without that input from companies that have realized that this is necessary, they will put the resources towards it. I think there's a real challenge to if an effort is being led wholly by academic exercise or academic experts or national lab experts or so forth without that kind of constant dynamic input from industry. So I just challenged that as you look at these standards, I think there is a role that, certainly standards organizations play, but hopefully they're playing a role in bringing together industry on things that are commonly needed. And I think there are issues like that in the advanced reactor space. But I would say if there's not adequate engagement from industry, it's probably not the key issue that needs to be addressed, because, otherwise the company would put resources towards it, because the company has to figure out the best places to put their resources. So it's kind of a perspective from, certainly there are limited resources all over, but there is an incentive from companies to come together to work on different issues. We do it all the time in different spaces. I think there are certain standards that different companies have seen fit to find useful and have put resources towards, and there's others that probably have not. And I wanted to address you. I know you mentioned it was kind of one of your first times hearing about it. I know this is kind of on a personal level, but I know we've been sharing with you some of this, and it's just a great opportunity now to get to share with a broader audience how we've been seeing some of these issues with the guidance. We shared kind of a lessons learned document with the industry in 2018 into 2019 after performing the pilot, and continue to present to the industry as much as we have opportunity after submitting our application and so forth. So really appreciate this opportunity, but hopefully we're communicating enough and often enough.
Well, I think Oklo can really provide a service to the entire industry. If you do share as much as you can and as frequently as is practical. And I'd like to offer my committee as a forum, as a convening forum for any such exchange. And certainly this community of practice sessions, would serve that role. But anyway, we do have other questions, and I'd like to just see how much of it we can cover, before we totally run out of time. So go ahead.
Okay. The question is from Robert Hayes. It's regarding compliance, and he had said it appears to be dependent on a single unit. Does the same safety basis apply to siting multiple units together in a single facility?
Yeah, it's an interesting question. How we've looked at our site is it's basically defined by the boundary of our building, and so we haven't looked at, for this first of a kind, for this design in particular, having more than one reactor inside the same building. Each one would have its own kind of power conversion system, and so even if they might be within a certain distance from each other, they'd be considered separate sites. So in other words, it's not like the NuScale plant, which is designed from the get-go to have like 12 reactors in a single pool and have kind of common safety systems, common coolant reserves or things like that. There's really nothing in common. So the PRA for that doesn't end up looking quite as complicated as you might be used to seeing.
Okay, thank you. Next question is actually from Rebecca Norris with NuScale. She had to drop off. She said, don't worry about her comment, but Caroline, if you're okay with it, I would like to email it to you. That way we get back to her, and that way we can move on as well. The next question again is from Robert Hayes. The question is, what if any options might exist for a current LWR to utilize one of these for backup diesel power? If any, what would be required to use their own spent fuel to power it? I'm sure you can clarify that.
Yeah, that's a really interesting question. Sorry, I don't know if you need to clarify. I'll just answer it, and then maybe you can clarify if you need to. Yeah, that was actually one of the very first things we were looking at back in 2013 was being backup power for existing LWRs. They're already on a site that's been well characterized, certainly. And they invest more than you might imagine, than some people might imagine. I think this group probably realizes, into their diesel generator sets. These aren't just things you buy at Home Depot. They're very high performing and have to be very resilient. And I remember talking to a utility executive about how much they were spending for tornado protection for their diesel gen sets. I think it was out in Missouri. So it's a very interesting concept. They can, in the meanwhile, sell the power, just leave the Aurora unit essentially on, sell the power when they need it, and then use it as backup when they need it as backup for safety reasons. So it is an interesting concept. We haven't seen that as like quite the viable kind of customer route as we thought it might be. Interestingly, back in 2013, there wasn't very much DOE money in advanced reactors, but there was in kind of existing fleet resilience. I'm trying to remember the name of the bucket of money, but basically that was a topic of interest. But really where we found the most near-term and most urgent customer need was in these remote areas where they're currently burning a lot of diesel. So that's still looking to be our first customers. After we kind of get this first unit built there at Idaho, we'll be doing follow-ups probably with some of those guys. So that's an interesting question. Yes, we would like to ultimately be part of fueling the plant from existing spent fuel. So it could be a very interesting concept ultimately and eventually. It'd probably take some time to fully implement that, but yeah, it's an exciting thing that we're looking forward to.
Well, let's see, at this point, since we're already past, well past 1 hour, I do want to make sure that, we have some limits on the amount of time that we spend in the community of practice sessions. So I think whatever other questions there are, there is one over there. I think I can just address it. And, but I do want to thank you, Caroline, for,
Thank you,
taking the time, and you have been very forthcoming with, answering all our questions. And I just want to express my gratitude on behalf of RP3C and ANS. So with that, we'll be in touch, and I would invite anybody that has questions, just please direct them to ANS, Pat Schroeder or myself, and we'll get back to you. And we're always welcome, any feedback on these sessions. So, please keep the feedback also coming. So with that, thank you, Caroline, and thanks everybody for participating. This has been a good session, and I hope you'll continue to participate in future. Thank you. Thanks a lot, Pat.
Thank you.
Take care.